Welcome to the deep dive. Today we're looking closely at EmbeddingGemma. It's a new text embedding model, lightweight, open, based on the Gemma 3 family, and it seems poised to change how we think about efficiency, especially if you're working with high-volume apps or need something for on-device use where resources are tight.
Yeah, to really get why embedding Gemma matters, you have to look at the current landscape. These text embedding models are, well, fundamental. They turn language into vectors, right? Which powers search, semantic similarity, all that. But the trend has been bigger and bigger models. We're talking billions of parameters. Think NVEmbed, Grit LM7B.
And hitting top benchmark scores with those big models is one thing. But it brings this huge challenge, doesn't it? This trade-off, performance versus cost. If you need speed, low latency, or deployment on, say, a mobile phone, those giant models often just aren't feasible. Too much memory, too much compute.
That's the problem space embedding Gemma steps into. It's quite compact, only 308 million parameters. The whole idea behind it is getting the best possible performance for the computational cost. It uses the Gemma 3 structure, but stays lean.
Okay, so that's the core question then. How does a model this small manage to compete with or even outperform much larger ones? The sources keep mentioning this innovative training recipe. Let's break that down. What are the key steps?
Well, the first part is a pretty clever initialization strategy. They didn't just take a standard pre-trained decoder, they started with a 300 million parameter decoder-only Gemma 3 model. But that was just the start.
Right, there was an intermediate step you mentioned.
Yes. They first adapted that decoder into an encoder-decoder model, kind of like the T5 Gemma approach, using the UL2 objective for pre-training. UL2 is versatile, good for teaching different NLP tasks. Once they had that encoder-decoder structure, then they initialized embedding Gemma using only the encoder part of it.
Taking an encoder that was derived from decoder, why go that route? Seems a bit roundabout.
It's about knowledge transfer, really. By adapting it to encoder-decoder first, they encourage the encoder part to develop richer, sort of more robust contextual understanding. So when they initialize the final embedding model from that encoder, it starts off with a better grasp of language context than if they'd use the original decoder or just random weights. And they tested that their ablation study showed this encoder-decoder initialization pathway was clearly better.
Okay, that makes sense. You're building in better understanding from the very beginning. So that leads to the next big piece. Knowledge transfer. How did they actually get this small model to produce embeddings similar to the big state-of-the-art ones?
They use a technique called geometric embedding distillation. Think of it as embedding matching. It basically forces the smaller embedding Gemma's output vectors to align with the vectors produced by a much larger, powerful teacher model, in this case, the Gemini embedding model. The student learns to map its outputs into the same kind of space as the teacher.
So it's learning the structure of the teacher's embedding space. Was there anything special about how they applied this distillation?
Yes, and this seems crucial. They didn't just align queries and their positive matches. They specifically applied distillation to hard negative passages, too. These are the tricky examples, right? The ones that are semantically close to the query but shouldn't match. By making the small model learn how the big teacher model distinguishes these hard negatives, they gave it a significant boost in discriminating fine-grained semantic differences.
That's smart engineering, focusing the learning on the toughest parts. Okay, let's talk structure. With a lean model, you need robust vectors, vectors that work well in the real world. Was there a specific mechanism to ensure that quality?
There was. They introduced a penalty during training called a spread-out regularizer. Technically, it's based on the second moment term of the global orthogonal regularizer, but its function is what's important for users.
And what does it do in practice?
Two main things, both related to how the embeddings are arranged in the vector space. First, it encourages the embeddings to be, well, spread out, not clumped together. This is really important for efficient retrieval using things like approximate nearest neighbor, or ANN, searches in vector databases. Densely packed vectors slow those searches down. Second, this spread-out approach improves the model's overall expressiveness and makes it more robust, particularly when you quantize the model, reduce its precision.
So it helps with training and deployment, makes the vectors easier to work with later. Now, the architecture itself, it's an encoder-only transformer, 24 layers. How does it actually produce that single vector output from all the token representations? What pooling strategy?
They went with mean pooling, just averaging the token representations from the transformer layers. Simple as that. And what's really interesting, kind of a key takeaway from their ablation studies, Table 3 specifically, is that simple pooling methods like mean pooling consistently did better than more complex ones. Better than attention pooling, even though attention pooling has more parameters it can learn.
That is surprising.
Yeah.
Usually the assumption is more complex attention mechanisms give you an edge. Why would simple mean pooling win here?
It might suggest the quality of the representations coming out of the transformer layers, thanks to the initialization and distillation, was already very high. Mean pooling is stable, computationally cheap, and maybe less prone to overfitting to the training data or the teacher model compared to attention pooling. It seems that simplicity, in this case, led to more robust and generalizable embeddings. The results bear that out.
A great reminder that sometimes the straightforward path is the best one, especially for deployment. One last detail in the training recipe, model souping.
Right. The final step involved model souping. They averaged the weights of several model checkpoints to get the final version. The interesting part here is what they varied to create the different checkpoints for the soup. Instead of just tweaking hyperparameters like learning rate, they averaged checkpoints from training runs that use different mixtures of fine-tuning data. These mixtures were optimized using Bayesian methods. It shows that souping works well by combining models specialized on slightly different data slices.
So that whole innovative recipe, initialization, distillation, regularization, simple pooling, smart souping clearly worked. Let's pivot to the results. How does this compact model actually perform on standard industry benchmarks against the giants?
They evaluated it pretty thoroughly. MTEB, the Massive Text Embedding Benchmark covering multilingual English code domains, also XOR retrieve and extreme up, and the results were really strong for its size class. EmbeddingGemma came out as state-of-the-art for models under 500 million parameters. That's across all the main MTB leaderboards.
And what about the aggregate scores? Sometimes individual task scores vary.
Looking at the aggregate metrics, board account, mean task score, mean task type score, it ranked first among those sub-500M models across the board. The board account is particularly indicative, showing consistent high ranking across many different tasks.
Let's put that into context, especially for something like multilingual performance, where model size often correlates strongly with capability.
Good point. On the MTB Multilingual V2 leaderboard, EmbeddingGemma ranks 8th overall, regardless of size, which puts it way ahead of other models in its weight class. It's 17 places higher than the next best sub-500 MEM model, so it's delivering performance close to models almost twice its size. That highlights the efficiency gain.
And given that efficiency is the goal, how well does it hold up when you really push the resource constraints? Did that spread-out regularizer help with quantization?
It seems so, yes. The performance remains strong even under significant compression. They showed it works well even if you truncate the output embeddings down to just 128 dimensions, saving a lot of memory. And crucially, it maintains performance even when the model weights are quantized down to very low precision, like 4-bit using quantization-aware training. In 4, in 8, mixed precision. It handles them well. That's vital for running on device.
And what about low-resource languages, often a challenge for smaller models? How did it do on extreme UPI?
Extreme up teased cross-lingual retrieval mapping content from 20 less common languages to English. Here, EmbeddingGemma didn't just do well, it significantly outperformed much larger models, including some commercial APIs. That really speaks to the quality of the foundation and the robustness of the embedding space they created.
So summing this up for our listeners, EmbeddingGemma seems to set a new benchmark for efficiency in text embeddings. It packs impressive state-of-the-art level performance into a very small 308 million parameter package. It really changes the expectation for smaller models.
And the key takeaway for practical application is clear. Its performance, its size, and its robustness to things like quantization make it extremely well suited for those low-latency, high-throughput scenarios, think edge computing, on-device AI. That's where this kind of model can really shine.
As you think about this deep dive, consider that interesting balance they struck. Sophisticated techniques like knowledge distillation, especially focusing on those hard negatives. But then combining that complexity with deliberate architectural simplicity, like choosing basic mean pooling over complex attention. It seems that specific combination, using complexity smartly for training and simplicity smartly for architecture, is what enabled such an efficient yet powerful general-purpose embedding model. Something to reflect on.